Hello and welcome. Today we're going to be talking about transformations of trig functions. Now, before you get into this video, you need to make sure that you have transformations of just general functions underneath your belt from the Year 11 course first. Because what we're going to do is we're going to relate this to a specific type of function. Why? Because they're sort of their own class of functions. They're very, very common, so it's handy to have the vocabulary behind them. But we're going to relate both of them together so we can understand. When I talk about the amplitude of a trig function, we're just actually talking about the vertical dilation. Okay. Now, in terms of everything, what's actually going to be happening is we're going to be really studying, right, and working our way up to be able to draw something that looks like that. That's our aim by the end of the next couple of videos to be able to do it. I'm going to break this down so that it's in a couple of different videos and we can work through it. Okay. So when we look at the transformations, okay, we're going to be using the terminology dilation, translation, and reflection. But we want to have some vocabulary specifically for the trigonometric functions out of the way first, okay? So short and simple, here you'll notice I have two trigonometric graphs, okay? One is sine x and the other is cos x, okay? We're very familiar with these. We've seen a lot of them before. What we want to do is we sort of want to understand the features of each graph. So first and foremost, you'll notice here I have the amplitude. The amplitude refers to the distance from the center of the graph to the peak, okay? So it's the distance from basically the middle of the graph all the way up to the top. We don't really say anything has a negative amplitude. We just talk it as being a magnitude. So in this particular case, with a basic sine and cos functions, you can see that the amplitude is 1. We're going here from y equals 0 all the way up to y equals 1. That's our amplitude. Next thing that we'd like to understand, you heard me mention the word center. So when I talk about the word center, okay, we're talking about this imaginary line that runs through the middle of a trig function, okay? And the easiest way to understand this is it's the mean value, okay, between the peaks and the troughs. Okay, so it's the mean value between the absolute maximum there and the minimum there. Okay, all right, so that's another bit of terminology for us. Okay, next thing is to understand the period. Okay, so the period of a trigonometric function is how long it takes to complete a full up and down motion before it sort of repeats itself, or basically how long it takes until it starts to repeat its own function again. So you'll notice here for sine, it goes up and then down once, okay, and then it would begin again, okay? So the period or the periodicity, okay, is from 0 to 2 pi. So we say that sine of x has a period of 2 pi. Same thing happening here for cos of x. It goes from up to down, then back up again, and then it would repeat that same pattern after 2 pi has elapsed. So we say that it has a period of 2 pi. Now, we're going to look at basically how each of these things shift throughout the day. There is one more transformation, which I'll get to in just a moment, that's known as phase shift, but we'll get there soon, okay? So, understanding everything, okay? First off, we want to use the terminology for amplitude, okay, as basically understanding it as a vertical dilation. When we go and change the amplitude of a trig function, all we're doing is we're stretching in the vertical direction or compressing, okay? We often use the letter A for amplitude, which is a little bit different to what we had before. And the easiest way to understand the amplitude is the distance from the center, which we talked about, to the max value. Something that's worthwhile noting, tangent does not have an amplitude, because it's approaching those asymptotes that shoots off to positive and negative infinity. So just being careful of that one, okay? The center, okay, that's affected by the vertical translation of the curve. That's if we add something onto the end of it, it shifts the curve up and down from the center, okay? It's a handy point for us to understand, and it's the mean value from the trough to peak. So how could we change the center? Well, we could take our y equals sine x, and then on the end, we could add a 4, and that would shift the whole curve upwards by 4 units, okay? All right, just as a bit of an example. Finally, the period, okay, is affected by the horizontal dilation, because essentially that's going to determine how many times our function is going to go up and down, okay, inside of a certain domain, right? But essentially, it's the length of time that it takes the trig curve to repeat its cycle, Okay, so sine x and cos x, as we've discussed before, have a period of 2 pi. However, tan, the curve, repeats every pi. Okay, so its period is half of that of sine and cos. All right. So when we horizontally dilate a function by the same factor, right? So for example, if we were to go and sketch y equals sine of 2x, that's a horizontal dilation, and it causes a compression along the x-axis towards the origin, right? We've understood this before as essentially causing 2 revolutions inside of 0 to 2 pi. Okay, but now what we're actually doing is we're understanding it as a horizontal dilation. Right, so when we go and do that, that's going to halve all of our values, our x values, bringing an extra, so we're going to double them out from 0 through to 2 pi because we halve all of our values from the scale factor. So how does that affect the period? Well, it's going to have 2 cycles inside of that now. Okay, so the period of this particular function, sorry, let me get an actual pen. The period is going to be equal to 2 pi, as that's our usual period for sine. And then we're going to halve it. So now sine 2x now repeats every pi. And you're going to see that happen in just a moment when we do a bit of an example. But this is just to sort of understand and get some vocabulary out of the way, just so we're ready to go. Okay. Finally, okay, depending on the number that we have, it affects our horizontal dilation. So we write the rule for cos nx and sine nx, okay, the period is equal to 2 pi divided by n. Okay, we have a cos 3x. That means it's going up and down 3 times inside of 0 to 2 pi. So it's going to take 2 pi divided by 3 for that cycle to occur. Okay, same thing for tan nx. I'll just fix that up. That is a tan nx. Okay, it's pi for tan. We divide it by whatever the number is, the horizontal dilation inside of that particular bracket to find it. Okay. So this might help us understand what's going on in regards to that. I mentioned just a moment ago what's actually happening. As you can see, we have cos 3x from 0 to 2 pi. It's going to repeat itself 3 different times, okay, as can be seen. All right, and that's why our period, okay, because remember, a period is just 1 cycle, is now divided by whatever the number is attached in front of the x, because we're causing a horizontal dilation, okay, to the original curve. Okay, now the final thing that we'll talk about is what's known as phase shift, and this is just a horizontal translation, okay, where we go and shift the entire curve left and right. So the variable that shifts the curve left and right often appears on the inside of the function. So for example, this is just our graph sine of x that's been shifted pi on 3 to the right. So we say this function here has a phase of pi on 3 to the right. Okay, so before we get stuck into everything in our next video, some handy hints that are going to help us out. Okay, always convert it to standard form so that we can identify what the phase is, okay, and our horizontal dilation, okay, before we go and sketch it. The other thing, don't change your curve when you're graphing. Try and keep the same basic curve structure if you can. All right, what you're going to do instead is you're going to change your scale, and it's going to help us keep things neat. Okay, and finally, on each curve we have 5 or so key points. We're going to use a table to sort of keep track of what's happening and make it very, very quick to go and sketch each of them. Okay, all right, I'll see you in the next video where we begin to do a couple of examples.